this section is devoted to the application of Bayesian inference. Especially people are interested how the Bayesian techniques can be applied in regression problems. So what we will do is that we will first of all consider the linear regression models and carry out our Bayesian inference, Bayesian analysis rather, based on that, and then extend this idea to the generalized linear mixed models. You know that you might have some idea about the generalized linear mixed models where the data nature are not continuous. So, it is not following the linear models, it is somewhat like the binary regression model, like the count regression model, and other kind of data nature are there. So, dependency on the covariates has to be looked into. So, in that case, how the Bayesian inference can be carried out, that is of interest to you and in fact to all the people who are interested in the Bayesian analysis. And finally, we will establish or we will demonstrate this thing through one nice live example that these parameters can be estimated by the Bayesian approach and the posterior inferences can be drawn accordingly. All right. So, in this second session, I would discuss with you the generalized linear mixed model. To know that, first of all, we should know what is generalized linear model. Incidentally, generalized linear model arises from the fact that when the responses or when the outcomes are of non-continuous nature, like the binary nature or the count nature, and some causal relationships are there, and one is interested in knowing the effect of that causal relationship through this model. So, it basically an extension of the linear model. Let us look at the linear model. A linear model specifies the relationship between a dependent variable y and a set of predictor variables x's, so that yi equal to xi dash beta, I being the subject. I am not bringing the error component, it is the relationship between the dependent variable and independent variables or predictor variables. Generalized linear model is a generalization of normal linear regression models to exponential family like normal, Poisson, gamma, binomial, etc. Now, I briefly say that way that it is basically a generalized linear model, or GLM is basically an extension from the linear model from two directions. One, the distribution of y can be non-normal and does not have to be continuous, and the second one is that the outcomes still can be predicted from a linear combination of x's, but they are connected via a link function. The DDE example, very standard example on the risk of cancer on the rats. I mean, the experiment has been done. In fact, you know that in the previous session we talked about the tumor development on the rats. It's basically the same experiment we are talking about. So, the scientific interest, does DDE exposure increase the risk of cancer? Test on rats been done. Let J index rat, dependent variables yi, binomial 1 pi or binary 1 pi, and pi is the risk of cancer for rat I, yi is binary, so it takes the value 1 when rat I is diagnosed with cancer or maybe tumor, and 0 otherwise. So, independent variables dose of DDE exposure, which is denoted by xj. Now, in generalized linear model, the likelihood function of y yi can be written this way, like for the binary model, we can write this at f yi given pi, which is pi to the power yi 1 minus pi to the power 1 minus yi. And then we write it in this, mathematical, for our mathematical convenience, we write it in this form, e to the power yi eta I over 1 plus e to the power eta I, where eta I being the log pi or over 1 minus pi or logit pi. So, this is how the logistic function serves as a canonical function, canonical link function in the binary setup. So, if you choose eta I, this your logit function log pi over 1 minus pi to be excited as beta, then the likelihood function here is e to the power, looking at the observations yi given pi has the density function this, we can write the likelihood function e to the power yi xi dash beta over 1 plus e to the power xi dash beta. Okay. Now, extending this idea of a generalized linear model to generalized linear mixed model, what you can see that in DD example, what is happening that the lab to lab variations are there. So, if the experiment is being done in several places in the country or around countries, different countries, so there is a variation in the laboratory environment. So, these variation can be taken into account or has to be taken into account into the model. So, there are unmeasured factors that vary between the different labs. So, lab to lab variation is represented by the unmeasured factors. For example, this variation may be lab to lab is due to the rodent diet, it is a rat diet. And GLMM is an extension of the generalized linear model, as I said, by adding random effects to the linear predictor. So, apart from the linear predictor in the canonical link, one can insert the random effect that takes into account the subject specific variation. So, let us look at this more extensively. The previous linear predictor is modified as eta ij xij dash beta plus zij dash bi, where I equals to 1 to n index lab, j equals to 1 to ni index rat within lab I. Beta are fixed effects parameters common to all rats, bi are random effects and the deviations for lab I. So, lab to lab variation is taken into account through bi. Now, GLMM basic model is through this predictor eta ij, as I said that xij dash beta plus zij dash bi. Now, if we choose xij equal to zij, then all the regression coefficients are assumed to vary for the different labs, because over all ij it varies. So, obviously, the regression coefficients vary from different labs, but on the other hand, if we choose zij to be 1, then only the intercept varies from different labs. So, lab to lab the variation is through the intercept term. Now, the computational part or ultimately the prediction or parameter estimation that can be done by using Gibbs sampling, that will be discussed in my third session. There are some advantages, some disadvantages like slow convergence. There are some other approaches like hierarchical centering, reparameterization, deterministic methods are available for logit and probit models. Also, EM algorithm can be applied, simplex method can be applied there. We will come to that later on, but before that, we go for Bayesian GLM, but we should first of all know what is Bayesian inference in the linear mixed model. So far I didn't consider the linear mixed model posterior analysis. Think of the model like y follows normal x beta plus z u. So what I am going to do, we first of all carry out the Bayesian analysis for the linear mixed model, then extend it to the generalized linear mixed model. That's my plan is. So y follows normal x beta plus z u, this is, I should say that y given u, because u is the random effect component. So given u, you have the mean x beta plus z u, and the dispersion matrix R. Maybe for simplicity you can take sigma e square I. Then you can write down the likelihood function given beta and u to be of this form like this. You know, the very standard form, normal likelihood y minus x beta minus z u prime R inverse y minus x beta minus z u, and then the constant terms comes up. Then this is the first stage where you define the likelihood. Go for the second stage where you define this, the prior. The subjective prior is beta, is p beta, which is beta follows normal beta naught and dispersion matrix v beta. The question arises about the choice of beta naught and v beta. We assume that these are all known, so subjectivity already arises there. Okay? And the structural prior is that u, which follows some density like u follows normal with mean 0, mean vector 0, multivariate normal mean vector 0, and the dispersion matrix is G, where G equal to A sigma E square. So A is known matrix. So we assume for simplicity that sigma, apart from sigma u square, the dispersion matrix of u is known to us. And this is the second stage priors, right? Now still there remains some hyperparameters like sigma e square and sigma u square in the second stage. So all these prior parameters are, I mean the parameters are there, hyperparameters are there. So for them we need to assume some priors. So I assume that sigma e square has certain prior pi sigma e, p sigma e square, and sigma u square has certain prior p sigma u square. Okay. So we then do the posterior analysis. We look for the joint posterior density beta u sigma e square sigma u square given data, and as I said that beta naught and v beta known to us, so we can write down the joint posterior density of all these parameters. Okay, and so this is basically, you see that this is the likelihood part, this is the likelihood part, this is the part of the prior for beta, then you take the prior for structural prior for u, and then you take the prior for sigma u square. This is the second stage prior, and prior for sigma e square. So we want to make full Bayesian probability statement for beta and u. How do I do that? Integrate out uncertainty on all other unknowns. So the unknowns are here because we have assumed prior for second stage prior for sigma u square and sigma e square. So we take integrate over that to get ultimately the posterior density of joint posterior density of beta and u given beta naught, v beta and data. Okay. Let's suppose that variance components are known. For the sake of simplicity, we assume variance components are known. So what we do is that now we assume R is known to us, G is known to us, beta naught, v beta earlier were known to us. So we write down this thing. So in that case, we do not need to take any prior for sigma e square and sigma u square, and only the beta and u are unknown. So we can consider the prior posterior for beta and u, and we derive theta is beta dashed and u dashed, w as xz, and accordingly the likelihood function, which is this, okay, and then the prior for theta is theta naught sigma, which is beta naught 0 and sigma is VB 0 0 g. So this is basically a block diagonal structure for the prior for theta, I mean for the dispersion matrix of the prior for theta. Okay. Then with this known variance component, the Bayesian inference can be done this way. We look for theta given theta naught sigma r y, the posterior density of theta now, marginal, I should say the marginal posterior density of theta, because there is no b here. So that comes out to be of the form given here, this exponent all, and this is proportional to the exponent of e to the power exponent of theta minus theta dash w dash r inverse w plus sigma inverse whole inverse theta minus theta hat. So theta hat can be computed to be this. A lot of derivations here. One has to sit with that in whole mind and can derive that thing. In other words, what we get? We get these beta and u. They have the joint posterior density given by this. So the interest is that when you consider a flat prior for beta, that means V beta tends to infinity or V inverse beta to be 0, tending to 0, then pi beta equals to 1, and in that case beta u has the posterior density like this, where beta hat and u hat is given by this form. Now the objective here was to show that whatever Henderson and Robinson suggested for small area estimation, the BLOP estimator. So this is basically the BLOP estimation of beta hat and u hat. That's very much useful in animal experiment. People use this quite extensively. So what we did here is, for the linear model, we apply this thing, these priors, and ultimately obtain the BLOP estimator in the classical setup. If one is interested in the BLOP estimation, like the posterior density of k prime beta and m prime u, one can easily see that this is the form that comes up. Okay, k prime beta marginally follows k prime beta hat and k prime c beta beta k. So this structure needs a lot of derivation, So now what we will do, we will go for extending this concept to the generalized linear mixed model. So in the generalized linear mixed model, as I said, the generalized linear mixed model differs from the generalized linear model in the sense that one additional term, random component, comes in the predictor, like in eta I or eta ij, whatever we have defined earlier, where you have xi dash beta or xij dash beta or xij dash beta, you need on top of that one additional random component. So now we look for, given the random component, suppose we have response measurements yij at time j, and given the random component, this is the mean expectation of yij given tij bi. So we can fit a model with random intercept. This is the link function g mu ij is beta naught plus beta 1 tij plus b naught I. In a Bayesian framework, we will need to assign prior distributions to bi, the structural prior we need to assign, and then beta naught and beta 1 and any other hyperparameters that may arise in the model. So we assume that flat priors for beta naught and beta 1, where normal 0 10 square is the, in both cases we assume the prior for beta naught and beta 1 to be normal 0 10 square. Interestingly, I said that these are flat priors, but I assume normal 0 10 square in both cases. The reason is that this is the basic strategy these days people follow, Bayesian people follow. is that they take the variance to be large enough for a normal distribution, so that it ultimately reduces to a flat or uniform flat prior. Okay? So even if the advantage is that for assuming normality is that it nicely matches with the likelihood, so that you can easily go for analytic development, or if not possible, then you can go for the computational development through the Gibbs sampling and other computational techniques. So anyway, the reason for considering the prior for beta naught and beta 1 to be normal is now clear, because variance is taken to be as large as possible, so that it reduces to a flat prior. We could assign prior for BI to be normal 0 tau square, in which case we would need to specify prior for tau square, maybe an inverse gamma 1 and 0.0260. Once again, this choice is because the variance comes out to be extremely large, so that ultimately reduces to a flat prior. Note that our likelihood is given by this, probably the Pyij given Tij Bi, so that Pyj given Tij Bi, if it is normal mu ij sigma square, then it is beta naught plus beta 1 Tij plus B naught I, and then we need to assign the prior distributions to these Bi beta naught beta 1 sigma square. Ultimately, the posterior distribution is proportional to this term. This term means the first term is the likelihood, the second term is the distribution of Bi given tau square, and the terms onwards, these are all the parameters for which we have assumed the priors. Recall that in Weinberg's, we need to parameterize the normal distribution in terms of the precision rather than the variance of standard deviation. So in that case, we would usually assign gamma priors to the precision variables. We go through an example. Xerophthalmia means basically an ocular manifestation of vitamin A deficiency. So this study is conducted in Indonesia to determine the causes and effects of vitamin A deficiency in preschool children. The question of interest is, are vitamin A deficient children at an increased risk of respiratory infection? Along with the presence of respiratory infection, basically we look into that, the presence or absence of respiratory infection. The following variables of interest were measured for 275 children for up to 6 consecutive quarterly visits. So it's basically a longitudinal type of observations, binary longitudinal data. And we have the covariates age, presence of xerophthalmia. This is the response or outcome, and then cosine and sine terms for the annual cycle, gender, height of age, and presence of stunting. The data set looks like this. You have respiratory infection, present or absent, age, xerophthalmia, whether this is, it's again xerophthalmia is present or in terms of presence or absence. Then the stunt time and the seat time, then the sex, age, all these covariates are there, all right. Since we are interested in inference at the individual level rather than the population level, we want to fit a generalized linear mixed effect model, that is a conditional model. Fitting a random effects model to the data allows us to address the question of how an individual child's risk for respiratory infection would change if their vitamin A status were to change. How will we do this? By allowing each child to have a distinct intercept which represents their propensity for infection. Then the conditional regression model is this: Yij, presence of a respiratory infection at visit j for child I mu ij, expectation of yij given xij and bi, and logit mu ij, because this is a binary response design. The logit function logit mu ij is bi plus beta naught plus beta 1 age ij plus beta 2 0 Pelmia for the ij, beta 3 is xij, and so on. All these covariates are there, all right. The prior specification is required. So what are the unknowns? The unknowns are bi, beta j's, and tau b. So once again, we in the variance of bi, the tau b comes up, and this is the hyperparameter. So we again take the prior for tau b, and we also assume that beta j follows normal 0, 10 to the power minus 4. It's clear to you that why we have taken that. The reason is that to get ultimately flat prior. So this is the situation for the prior. Then with this we use the Bayesian methodology, and the inference obtained using the Bayesian GLMM will be at the individual level, because for every I, for every individual I, we are able to determine that. You know that when you consider the posterior density of bi given all other parameters, or bi given the data and the known parameters, then it's basically the inference at the individual ith level. If you hate Windbugs, you can go ahead with the using R, because in R also this is available. So one can instead of analytically going for the posterior distribution and the posterior inference, which is very difficult to do, we can through R or Windbugs, we can use the Bayesian computation technique to ultimately generate observations from the posterior distribution of interest, and can then based on that compute the posterior means, posterior variances, and other things. I think I would stop here, and in the next part I will go for the Bayesian computing technique. All right, 5 minutes. So guys, what I discussed with you in this section is the application of Bayesian inference in linear models and generalized linear models. What is happening is that in the linear models, I should say on the other way, there are linear mixed models where the random components are there. The proper prior has to be taken, and then the posterior analysis can be done. Because the linear models, in linear models, the error distribution is assumed to be normal, conjugate prior serves nicely, so that posterior inferences can be drawn analytically very easily, I should say. On the other hand, if you consider the generalized linear mixed models, where the link function is non-linear, like in the binary setup you have the logit say regression, then in the count data you have the log linear model and other things. So what is happening, the link function is non-linear, and so straightway the Bayesian analysis cannot be done analytically, I should say. So we must take help of the computational approach, and in fact I will show in the next section that how the Bayesian computation technique can be applied to resolve this issue. So we discussed till the development of the model, generalized linear mixed models, and the setup where we are ready to apply the Bayesian computation technique. All right.